All right. Energy conversion. Examples of energy conversion for making electricity. We're always trying to make electricity. Why are we always trying to make electricity? Well, because we can store that easily with batteries. That's the reason why we want to make electricity. And then we can use it in a bunch of different ways. It's very versatile. These are all the ways that we are the most common ways, I guess, that we make electricity or get electricity. We've talked about all of these before, so I'm going to continue over this. We talked about vehicle system conversion. We want, what was that? We want mechanical energy less than heat. I mean, we do want heat coming through like the vents in our car in the winter, but mostly we want mechanical energy just because uh, we want to go. That's the whole point of a car. Efficiency, how to calculate efficiency. This is what you would maybe think of anyway. The symbol here is eta, E-T-A. You pronounce it's kind of like theta, but eta. It looks like an N with a really long second leg, I guess. It's the percentage of the input energy that is transformed to the output energy. So in the desired form, that's what you want. So you're not thinking of the total output. The total output should be 100%, right? The total, where was it? There. Can't be created nor destroyed. So the energy input is really going to be the same as the energy output. However, the efficiency is the percentage of the input energy that is transformed to the output energy in the desired form. In the desired form, that's the key part. So the amount of energy that you put in and the amount of energy that is useful to you is the output energy. So eta, ETA, eta is just the fraction E out divided by E in. Usually it's presented as a percentage, so you multiply it by 100. So we'll be calculating efficiency for some things. What are energy concerns? This is like a worldly question. We are concerned about pollution, depletion, dependency, and cost. A lot of engineers, they have not just like, okay, how do I do this, but how do I do this and reduce, these things. That's the real problem solving. So that's what our engineers are doing. Power. What is power? This comes back to the first slide. Power is a rate, and it's the rate at which energy is expended over time. So it's just energy, which is work, or it's measured in joules. It's energy divided by the time it took to expend that energy. The weird part about this is sometimes we use E for energy, which would be in joules, because it's the same thing as the work, because work is energy, and it's also in joules. Anytime you see a W all by itself, it's talking about work. Anytime you see a W next to a 1, it's talking about power, and the standard unit for power is a watt. That's why it's W. So 1 watt, by definition, this is also something you should write down. I'm probably going to go back and tell you what you should write down. 1 watt is 1 joule per second. Remember, it's a rate, so it has to be something per some unit of time. So 1 watt is defined to be 1 joule per second. And yeah, let's go back to that first, no, not yet. Electrical power, use electricity to do work, use mechanical energy to do work, fluid power, that's very nice. Oh, we get to actually study hydraulic and pneumatics systems. That'll be fun. All right, let's go back to that first example. A student lifts a 50-pound ball 4 feet in 5 seconds. So we already actually calculated the what was it? The work done in joules. I think it'll say yes. So the work done in joules was about 271. That's what we got in the other slide. Now to calculate the power, what do you think you got to do if you're going to use these formulas? Well, you already have the work, which is 271 joules, and we have, is it in seconds? Yes, 500 seconds. So we just divide the two. It's easy calculations. So the power, which will be in watts, joules per second, right, The power is 271 joules. That's the work done, or the energy expended. And then the amount of time it took was 5 seconds. You divide that. So to answer this question, how many watts of power did the student use to lift the ball? 54.3 watts. Easy. And that's the end. Happy day. Sorry this was such a crappy video. Let's stop it, huh? Yes.